Hey everyone, today we're going to be talking about limit laws, and we're going to go over some functions and that are going to help us understand limits better. And then finally we're going to understand squeeze theorem, which is, we're going to get into that later. But before that, there was something that I mentioned in the previous video, which was about this function right here, 2x over x minus 3, when I had for left hand limit x approaching 3 minus for the left hand limit sign, I switched it with h tending to 0. I switched it with another variable. So before we get into limit laws, I just want to address that real quick. So if you just look at the number line here, right? This is 3, right? This is x. Let's look at the left hand limit first. So x is approaching 3 from the left hand side, right? So let h be the distance between 3 and x, right? Okay, so for the left hand limit, which is greater, 3 or x? 3, right? So the distance h is going to be 3 minus x. That's going to give us the distance h, right? So h is equal to 3 minus x. In terms of x, we write this as x is equal to 3 minus h. So when x is going to approach 3, this distance h, it's going to approach 0, right? That's why when x is approaching 3 from the left-hand side, I switch it with h tending to 0, and I switch wherever I had my x with 3 minus h, hence this, right? And then I solve it further in the previous video. Similarly for the right hand limit, now x is approaching 3 from the right hand side, which means x is going to be greater than 3. So in order to calculate h, which is the distance between 3 and x, that's going to be x minus 3, which is going to give me this distance h over here. So I have h is equal to x minus 3. In terms of x, I write this as 3 plus h. And that's literally what I did. So I have x tending to 3 plus, switch it with h tending to 0, and wherever I had my x, I switched it with 3 plus h, right? Okay, that's all. Let's get into limit laws. And limit laws are pretty straightforward. They are intuitive, they make sense, and they don't get you're not going to get super difficult questions pertaining to limit laws. All right, so let's say you have a function h of x, which is a combination of two other functions, f of x and g of x. So you have f of x plus g of x, which is equal to h of x. So what limit laws tell us was that if I have this operation, limit x approaching a for h of x, I can write this as limit x approaching a, f of x plus g of x. So limit laws, right, they tell me that I can write this as this. Limit x tending to a, f of x, plus limit x tending to a, g of x. So limits are supposed to be thought of as a operation, right? Just like when you're doing multiplication, you can use the distributive property, right? If you have 2 times bracket 3 plus 6, you can write this as 2 times 3 plus 2 times 6. So it's kind of similar to that, but not exactly the same thing. So here I use addition. I can use subtraction. So then this would be fx minus g of x, and then this would switch to limit f of x minus limit g of x. Again, if I have multiplication, let's say h of x is a multiplication of two different functions, f of x and gx, then again I can just use the multiplication symbol. If they're a division, then I can simply divide them. And finally, if I have something of a scalar multiplication, what that means is that, let's say h of x is c times f of x, right? Where c is a scalar. So scalar means that it's not a, so let's say this is a function of x, right? So that if it's x squared, right? Then h of x, let's say f of x is x squared. C would mean 2 times x squared, or 3 times, minus 5 times, 1 over 3. So that's a scalar, right? That's a scalar quantity. So that's c of f of x. So then I write limit x tending to h of x is going to be limit x tending to a c times f of x. And since my limit operation is on x, right? So if I have 2x squared, there's no x term in 2, right? 2 is just a scalar, right? So what I can do is that I can take the c out and I can write it this way. Limit x tending to a f of x. So let's just look into an example of what that would look like. Okay, let's say I have a function here, x squared plus 2x, right? So again, this is going to be f of x, let's say, and this is g of x. And using the scalar 2, this means it's 2 times g of x, right? So if I want to find the limit hx at x tending to 1, right? How am I going to write this? I'm going to write this as limit x tending to 1, x squared plus 2x. Limit laws tell me I can write this as x tending to 1, x squared, plus 2 times limit x tending to 1, 2 times x, right? I took the 2 outside. So this is just going to be 1 plus 2 times 1, which is 3. So this is my answer, right? So like limit laws are like, they tell us like we can use limit operations as just operations, simple operations, and they work with addition, subtraction, multiplication, so on. Let's look at another example, and we're gonna understand left and right hand limit now a little better. Let's say I have this function g of x, which is a piecewise function, which means that it's gonna take different values at different values of x. So this is what it looks like. This means that when x does not equal to when x does not equal to 1, this function is going to be x plus 1. But when x is equal to 1, this function is going to take pi, right? The irrational number pi. That's the value this function is going to take. So if I'm asked to compute the limit for this function at x is equal to 1, right? Evaluate g of x at x is equal to 1. Limit for g of x as x is equal to 1. How do I do this? Well, simply I use the left term limit, which is going to be limit x tending to 1 minus g of x in terms of h, right? Like this is the thing that we covered right in the start of this video. I can write this h tending to 0, which is just going to make this g 1 minus h. And then I have limit h tending to 0. So g, right, I have 1 minus h, right? It's not equivalent to 1, right? X does not equal to 1. This means that I'm going to take x does not equal to 1 value. So then when I plug in 1 minus h in the function, I'm going to get 1 minus h plus 1. And I plug in h is 0. I'm just going to get 2. Right? That's the value I get. For the right hand limit, similarly, I have x tending to 1 plus now, g of x. H tending to 0, I make this 1 plus h now. And now this is going to be the same, h tending to 0, 1 plus h plus 1, which is again 2, right? So, we covered this in the previous video, that limits are not supposed to be thought as like when x is equal to 1, right? That's not what we're discussing, because at x equal to 1, it's going to be pi. However, when x is approaching 1 from the left-hand side and from the right-hand side, the value that the function is going to take is x plus 1. That's why the value that we're getting is 2. However, since the left-hand limit and the right-hand limit are the same, we can say that the limit does exist for this function, and it's going to be 2, right? Okay, now let's look at another function. Let's say we have this function f of x, which is equal to mod x divided by x. Now I'm assuming you guys are familiar with how the mod function works. Okay, so I have mod x is equal to x. Let's draw the graph for this function. Let's understand this function using graphs. Okay, so this is what the graph for this function looks like. What this means is that at x is equal to 0, which is the y-axis, right? X is going to be 0 at y-axis. This function is not defined. It's going to be 0 over 0, which is not defined. So that's why we have the empty circle here. However, for positive values, something like, let's pick a number. Let's pick 5. So I have mod of 5 over 5. Mod of 5 is just going to be 5. Over 5, that's going to be 1. So for every positive value this function is going to take, for every x greater than 0, we know that the value the function is going to take is 1, right? It's going to be at this line, y is equal to 1, right? Because the numerator and the denominator are going to be the same. However, for negative values, let's say you'll take negative 2, right? The mod operation is going to make that negative 2 into a positive. So that's going to be positive 2. Divided by x, and x was negative 2, right? So that's going to be 2 over negative 2, which is negative 1, which is this line right here. So for x less than 0, which is on the left-hand side of the y-axis, we know that the value is just going to be y is equal to negative 1, right? That value is always going to be negative 1. And for the positive x value is going to be y plus 1. So if I'm asked, what is the limit? Limit x approaching 1, f of x. X approaching 0, right? If I'm asked this, f of 0 is not defined. I know f of 0 is not defined, right? That's not possible. We can't find that because that's going to be 0 over 0. However, we can find the limit. And limits are not the same as, plugging in that value. So I have x tending to 0, f of x. If I'm asked to find the left-hand limit, right? Let's see what the left-hand limit. The left-hand limit is going to be the value that x, the function takes when x is approaching 0 from the left-hand side, which is going to be this side, right? So, and we see that the value is going to be -1, right? For when x is something like negative 0.001, right? Something of that sort, it's going to be -1 because that's the value we're going to get when you plug that in. However, for the right-hand limit, we're going to get something, let's take a value like 0.00001, positive, right? So that's going to be 1. So we know that the left-hand limit and the right-hand limit are not going to be the same because when x is approaching 0 from the left-hand side, the value is going to be -1. From the right-hand side, it's going to be 1, which means the left-hand limit and the right-hand limit are not the same, which means that this limit for this function when x is approaching 0 does not exist. Okay, now let's look at another function. Let's say, and we're going to solve this one out. Okay, I have this function f of x. Or let's switch it a little. I have f of t, which is this function, root t squared plus 9 minus 3 over t squared. I have this function. I'm asked to find the evaluate limit t tending to 0 f of t. Right, this is what I'm asked. How do I do that? I can take the left and right hand limit, but I'm just going to go with my gut and see what I get when I just take the overall limit, right? Limit t tending to 0 f of t, I'm going to get limit t tending to 0 root t squared plus 9 minus 3 over t squared. Now I'm going to use something called rationalization. I'm pretty sure you guys are familiar with it if you covered functions. It's basically you use the algebraic expression a squared minus b squared is equal to a plus b times a minus b, right? You use this expression. How are we going to use that? Well, I see that I have this root in the numerator. How do I get rid of this? If I have, if let's assume this is my a and 3 is my b, then this would be like a minus b, right? I can multiply the numerator and denominator by a plus b to get a squared minus b squared. And that would help me get rid of this root right here, right? Let's do it. So I have, this would imply limit t tending to 0, root t squared plus 9 minus 3 over t squared times root t squared plus 9 plus 3 over root t squared plus 9 plus 3. So I can multiply both the numerator and denominator by the same term, right? That's allowed. So I get a minus b times a plus b in the numerator. So that's going to be limit t tending to 0. I'm going to get a squared minus b squared. So a is root t squared plus 9. The square is going to be t squared plus 9 minus b squared. b is 3. It's not -3, it's 3, right? So that's going to give me 9. And the denominator is going to be t squared times root t squared plus 9 plus 3. I can cancel out these 9's in the numerator. I'm going to be left with a t squared in the numerator and a t squared in the denominator. I can cancel those out as well. So I will be left with 1 over root t squared plus 9 plus 3. And I see that if I plug in t's, the value of 0, because initially I was not allowed to do that, right? Because I had this, because when I plugged in t is equal to 0 in the function, I was going to get root 9 minus 3 over 0, which is 0 over 0, which is not defined. That's why I had to use the limit here, right? That's why I used rationalization. If I had x squared and limit x approaching 0 for x squared, I would just plug in 0 and I get 0, right? However, here I'm going to get something like 0 over 0, which is undefined. That's why we went through all this trouble to rationalize it and to get something that's not going to result in something undefined. But when I plug in 0 now, I'm just going to get 1, right? Because that's all that's left in the numerator. And denominator, when I plug in 0, I'm going to get root 0 plus 9, which is 3, plus 3. 3 plus 3 is 6. So this is my limit. That's how you evaluate limits. Okay, now let's look at another function before we go on to discuss squeeze theorem. So this function now is called the greatest integer function. It's written as this with 2 brackets, or you can also write it as just this, right? So what this basically is that, let's draw a graph for this function. It's going to be like this. Like that. What that means is that my bad. These dots, they make a lot of a difference, these empty circles. So what this means is that if I have x is equal to 0, I'm just going to get 0. If I have x is equal to 0.7, I'm going to go to the left and find the next integer. So 0.7, I'm going to the left, I'm going to find 0, right? For x is equal to 7, I'm going to find 0. Okay, how about x is equal to 1? That's again going to be 1. For x is equal to 1.5, that's going to be around here. I'm just going to go to the left and I'm going to find 1. So for any positive values we're talking about, right? If we have 2.7, 2.8.9, 2.99999, those are all going to go to 2 because you're going to go to the left and find the integer. For negative values, however, you're going to see a difference, right? Because it's going to be the opposite. If you have opposite how? Let's see. If I have negative 1.7, right? I go to the left, just imagine the number line, just imagine the x-axis. Negative 1.7 is going to go to the left, and that's going to give me negative 2, not negative 1, because that's going to the right, right? Let's say I have negative 47.36. Again, I'm going to go to the left, and I'm going to find negative 48. That's how it works. So this is the greatest integer function. It's going to find the integer value that's to the left of whatever non-integer value you take on. But for integer values like negative 5, negative 6, negative 7, 0, 5, 3, 2, whatever, those are just going to give you the integer you plug in. Okay, so if I'm asked, what's the limit for this function f of x, let's just call it f of x, when x is approaching 2, right? If I'm asked this question, I'm going to go look at the left-hand limit first. When I look at the left-hand limit at x is equal to 2, so this is 1, this is my x is equal to 2, right? So at x is equal to 2, which is like right here, actually, this value, I see when the limit is going to approach from the left-hand side, which is going to be like 1.99999, right? When I plug that in here for the function, that's going to bring me all the way to 1, right? So the left-hand limit, when I plug in 2, that's going to be 1. For the right-hand limit, however, at x is equal to, when x is approaching 2, it's going to be 2.00001, something, or like super close to 2, but not exactly 2. That's going to take it left, and the left is going to be 2. So I see that the left-hand limit and the right-hand limit are never going to be the same for integer values. So if I took 2 here, if I take negative 3, for instance, what's going to happen for that, at that value for this function? Then if I take the left-hand limit, that's going to be negative, left of negative 3 is going to be like negative 3.00001, right? That's going to go all the way to the left, and that's going to go to negative 4. If I take negative to the right, so negative 2.999, that's going to go to the left, and that's going to be stuck at negative 3. So the left-hand limit and the right-hand limit are not going to be equal for this function, greatest integer function, at any integer value, right? So this means the limit for the greatest integer function does not exist at integer values. We now understand that. Now we're gonna understand squeeze theorem, which is pretty straightforward, but it's an important technique that helps us understand and figure out certain limits that are kind of hard to find. So let's say I have something like f of x is equal to x squared times sine 1 over x. And the squeeze theorem, that basically means is that if I have one function that's greater than my said function like f of x, right? Let's say I have a g of x, which is greater than f of x. And I have an h of x, which is smaller than f of x. And if I can find the limit, so let's say I'm finding the limit of f of x at x equals 0 when x is approaching 0. If I can find the limit for these two, I can say that the limit for this function is going to exist between those two, because that's how the limit operation works, right? That's how we understood limit laws, that limits, like limit x tending to some a, that acts like an operation and I can plug that in. So if you have something like 2 is less than 3 is less than 4, I can multiply all three of them by 2 to get 4 is less than 6 is less than 8, right? I multiplied all 3 by 2. Similarly, I can use the limit operation to do that. How? Let's see. So I have this function x squared times sine 1 over x. And when I plug in 0 here, I know I'm going to get 1 over 0 for sine of x, which is undefined. So I can't do that, but we can find the limit. How do we do that? Let's see. So I know that, you know, sine of x, sine of whatever I have, sine of 1 over x, for instance, that's not going to be greater than, it's going to lie between -1 and 1 because that's how the sine function works. So that's always going to be between these. And if I multiply all three sides by x squared, I'm going to get negative x squared is less than equal to x squared times sine 1 over x is less than equal to x squared. Now I can use the limit operation. So I have limit x tending to 0 minus x squared is less than equal to limit x tending to 0 x squared times sine 1 over x is less than equal to limit x tending to 0 x squared. I can find, I don't know what this is, but I can find this one and this one pretty easily. This is just going to be 0 and this is going to be 0. I plug in 0 for x squared, I plug in 0 for minus x squared, I'm just going to get 0. So I know this limit is going to exist between 0 and 0, which means it's obviously equal to 0. So this limit is just going to be 0. I found this limit using squeeze theorem because I know that these two functions are greater than or less than equal to this function that I have, f of x, and I can find the limit for these two, and I know that the limit is going to exist for between these two numbers, right, between these two limits, and those turn out to be the same. There's both of them turned out to be 0, so I know that the limit for this function is just going to be 0. So the graph actually for this function looks like this, right? And this is x squared, this is minus x squared, and the graph for x times minus x times x squared times sine 1 over x looks like kind of like that. I'm just drawing roughly, but it's going to oscillate between these two graphs. So at x equals 0, this is the value it's going to take. That's the limit value it's going to take. Correction. So that's what the squeeze theorem, that's how it helps us deal with a lot of problems. That's how squeeze theorem helps us understand certain limits that are harder to understand. And that's all for this this video. We're gonna go over the precise definition of limits in the next class, which is a kind of a theoretical concept, but we're gonna go over a bunch of different examples to better understand how it works. And stay tuned for the next video.